Hello and welcome to the lecture for section 1.2 and 3 on sampling. Statistics, as we've said before, is the science of drawing conclusions from data. But of course our data has to come from somewhere. So whether we are involved with an observational study or with a designed experiment, we almost always have to do some kind of sampling. The reason for that is that whole populations are typically too big, too expensive, or simply they are inaccessible and therefore we cannot study the whole thing. It's therefore essential that data be taken from an unbiased sample. The opposite of saying that a sample is biased is to say that it is representative. The sample must represent the entire population accurately. Bias then means systematically favoring one or more outcomes, and our goal in designing our sampling technique is to avoid that situation. Let's think about this example. Suppose that we wanted to take a national survey to determine the current approval rating of the President of the United States. Now, there are well over 200 million people in the United States, and it simply wouldn't do for us to ask that question from every single person. The population is simply too big. It would also cost a tremendous amount of money to try to do that, and in fact it's really not even possible. A number of people in the population do not wish to talk to us, and even if we were willing to invest the kind of time and money that it would take to talk to everyone in the United States, what we would find is that it would take so long that by the time we finished our survey, people's opinions would have changed, so that it is literally impossible to get a snapshot of people's opinion within a short period of time if we wanted to talk to everyone. Now, as soon as we come to the conclusion that we take a sampling of the population rather than to speak to the whole population, then we realize that we're going to have to be careful in how we choose the individuals that are in our survey. It wouldn't do, say, to stop at several shopping malls and just talk to the people who are coming in and out, because then we would only be talking to people who are shopping in shopping malls, which is exactly the opposite of what we want to do. So how can we choose individuals to be in a sample? Well, one of the first things that many people will try is called a voluntary response sample. Now that means that each subject, each person decides whether or not they're going to be included. Voluntary response samples are virtually always biased, and the reason is that respondents with the strongest feelings are most likely to participate. You'll hear this occasionally on popular radio or television stations. Some kind of a question will be posed to the audience, and they'll be encouraged to call a certain number or visit a website to record a vote for whether they agree or disagree with a certain statement. There was a famous example of this that occurred a number of years ago. I think it was in around 1975 or 76. The writers of the Ann Landers column posed this question to the audience: if you had to do it all over again, would you have children? The shocking result was that about 70% of her respondents said, no, if we could do it all over again, we would not have children. Now, most of us probably think this is not a reasonable representation of the way most parents feel. Certainly, we hope not the way that our own parents feel. And that intuition turns out to be correct. In a follow-up popular study out of a magazine, people were asked again to volunteer and respond how they felt about it, but this time they were informed ahead of time of the 70% result that Ann Landers had gotten from her column. This time about 95% of the respondents said that they would have children. Well, what could be happening here? How could it possibly be that in a short period of time, 70% of the population of parents first think they wouldn't have children again if they could do it over, and then within a few months they've changed their mind and now 95% of them say that they would? Well, the reason is that this is a voluntary response sample, and people choose to respond or not according to their feelings at the moment. In the first case, most people reading Ann Lander's columns didn't really feel strongly about this issue, so those who responded were those who probably were having some considerable difficulties in their families at the moment or sustained over time. Those people, not surprisingly, said perhaps it would be a good idea if we'd never had children in the beginning. Then, reading the magazine article, other people were responding negatively to the news that 70% of parents apparently didn't want to have their children anymore. And because of those negative feelings, 95% of them responded probably with vigor that they would have children. You see, the issue here is that the subjects are choosing themselves whether they're going to be in or out of the sample, and this almost always will attract only the people with the strongest feelings. And furthermore, the strongest feelings are almost always feelings that are negative in one respect or another. So how should we go about getting a sample that won't be swayed in one direction or the other? Well, there are a number of methods, but the real gold standard of sampling is known as the SRS, the simple random sample. Now, a simple random sample is a sampling procedure for which each possible sample of a given size is equally likely to be the one that is chosen. A simple random sample is one that is obtained by simple random sampling. Now, there is one distinction we need to make when we're doing a simple random sample, and you do want to pay attention to that, and that is whether we're doing sampling with replacement or without. The standard is always without replacement unless there is some strong reason to do otherwise. These selections are made by, say, a mechanical device, a table of random numbers, perhaps a computer or a calculator, a program for selecting random digits. These devices are known as random number generators. Let me give you an example of how this might work out. Let's suppose that we wanted to take a simple random sample of size 5 from our statistics class. Now, since we're doing this by video and we don't have a live class, let's make this assumption. There are exactly 30 people in our class. So what we're going to do is label each individual with a pair of digits. It's important that each person get the same number of digits. We don't want to label them as 1, 2, etc., then 10, 11, on up to 30. The reason is that the people with the lowest numbers, 1, 2 through 9, will have a higher chance of being selected, or perhaps a 0% of being selected, depending on how we're going to interpret the digits that we come across in our table. Then we're going to choose a method for reading the table. Well, that means you choose a place to start and a direction to read, and you'll see how we'll do that in just a moment. Then we simply take the consecutive labels that actually refer to someone in the group, discarding all the others, and that will allow us to choose a sample. So let's say in this case I've shown you here a page out of a table of random digits, and with the yellow pen I've circled the part of the table that I'm going to be using. Now, the way we would choose that, of course, has to be at random. One way that people will do this is maybe they'll close their eyes, put their finger down on the table at random somewhere, and they'll choose to start on the row that their finger rests on. That may take a bit of interpretation if you seem to be on more than one row. That's probably not terribly important because all of the rows, all of the columns are simply random digits. But you don't want to do the same thing every time. That would defeat the purpose of using the table. So let's suppose that somehow in this case we have selected the fifth row as the place we're going to start, and we're going to be reading from left to right. We will take 2 digits at a time. Now, as we do that, then we'll start right here, and those first 2 digits appear to be 3, 1. Now, the labels for the people in our group are going to be 2-digit labels, starting with 0, 1, then 0, 2, etc., and running all the way up to 3, 0. So 3, 1 does not refer to anyone in our class, and therefore we simply cross that out, at least mentally, and we discard it. 4, 6 is the next pair of digits. That also does not refer to anyone in the group, so we discard that. Then we will move on to 6, 4. Notice that that means that this gap here between the columns is not considered significant for interpreting the digits. It's only there to help us read the table. So the first labels we encounter are 3, 1, then 4, 6, then 6, 4, then 3, 7, then 6, 1, 9, 4, 8, 7, and finally 2, 9 is a valid label for someone in our group. So the person who is labeled 2, 9 is put into the sample. The very next two digits, 2, 2, also are valid. That person goes into the group. The label 3, 0 is valid, and that person goes into the group. The very next one we encounter would be 0, 5, so the fifth person in our group will also be put in, and at this point we have 1, 2, 3, 4 in our sample. Continue reading from left to right and then from top to bottom. We finally encounter 0, 9 as the next valid label. Now, this is a good opportunity to discuss a subtlety that comes up with using a table of random digits, and that is, remember, we're doing without replacement, which means that you'd never select someone twice for the sample. So suppose we had been trying to get not 5, but rather 6 in our sample. Well then, the next thing that we would encounter here would be 3, 0, which is a valid label. However, the person labeled 3, 0 was already selected. So what we mean by without replacement is we are thinking when we selected the first person that we took them out of the pool of candidates. So at this point, the second time we encounter the 3, 0 label, that's not considered valid, and we would go on to 0, 4, and 0, 4 would be selected and put into our sample. So this is how we use a table of random digits. Just to make this absolutely clear, there is no reason that you can't read it from right to left rather than from left to right. There's no reason you can't read by columns rather than by rows, and that could be from top to bottom or from bottom to top. And you could even consider different rules for proceeding, say, from one row or column to the next. So I could, for instance, choose to start with this column here in those labeled 10 through 19 and read down. When I get to the bottom of that, I could then proceed by going back up. If I haven't got everything I need by then, I could go back down and take this kind of a weaving pattern. Or I could choose ahead of time that I'm going to always read down. So I'd read the first one down. If I still need more labels, I'd then proceed to the next one and read that one down, etc. The only requirement is that we decide on the rules before we start reading digits. That way, our judgment about which labels will be selected is not influenced as we watch the numbers being selected. One of the reasons that we actually use a table of random digits is that if people try to choose digits randomly, they'll almost certainly not be able to do that. What tends to happen is if we start picking numbers and we start to see what looks like a pattern developing, most of us will then deliberately start doing something to try to break that pattern. And that's why the random number generator or the table of random digits actually helps us to avoid bias as we select those digits. Now, in real-life statistics, software is much more convenient than random number tables. And if you think about it, there's a pretty simple reason for that. Most of the survey data that we see being reported in the news involves at least many hundreds and oftentimes thousands of people in the sample. It really wouldn't be very convenient to have books of random digits and have people sitting in rooms reading off row after row of these, trying to come up with digits that are in some way valid and useful for some selection scheme of people. So it's just simply the large number that have to be handled. Nevertheless, being able to read these tables is helpful for small samples, and it does help us to get an idea of what's involved. Let's think about going back to the idea of a simple random sample. We just talked about how one could be selected, in this case with a table of random digits. Let's think about another strategy. Suppose we have a student sitting in a classroom, and maybe we have, let's say, 5 rows of desks or chairs, and what we do is we randomly pick a number between 1 and 4, and suppose that turns out to be a 2. And then what we're going to do is on the first row, say looking from the front of the class at the faces of the students, we'll choose the second person sitting in the row as we look from left to right. So the second person from row 1, the second person from row 2, the second person from row 3, etc., until we get through all of the 5 rows. Would that be a simple random sample? Well, let me just let you think about that for a moment, and then we'll answer. Okay, the answer is no. That is not a simple random sample. Let's back up to our definition and see why that would be. A simple random sample involves a sampling procedure for which each possible sample of a given size is equally likely to be obtained. If we're going to use this method that we've described, it is necessarily the case that we get one person from each of the 5 rows. Well, is it then possible to get a sample that has, say, 2 people from the 3rd row? Well, it certainly isn't. But a simple random sample is supposed to come from a procedure that makes every possible sample, in this case of size 5, just as likely as any other. And we certainly ruled some out completely. So that means that that is not an example of a simple random sample.